In this set of slides, we're going to be looking at current voltage relationships and also non-ohmic devices. So just to recap, previously what we had on this slide is a perfect current source, which is what we're using usually in a lot of the problems, as it's the circle with the arrow coming through and a current I coming out, is a perfect current source. So on a current versus voltage plot like this, that comes out as a horizontal line. The current, let's just say it's giving 1 amp of current, it is always giving 1 amp of current. Doesn't matter what the voltage is. Same with a perfect voltage source. So perfect voltage source, like the batteries we're using or any of the circuit diagram pictures for voltage, what we're presuming is that always gives out a constant voltage no matter what the current is. So if it's a 9-volt battery, we're saying mathematically this is always going to give out a 9-volt source no matter what the current is that is being supplied to the rest of the circuit. And what we're also saying then is a resistor here, R, is a function of voltage and current, which is linear. And so the slope equals 1 over R. And essentially that's saying that as the voltage goes up, the current goes up as well, as it's a linear relationship. But these are all mathematical approximations, and the real world doesn't actually look and work this way. So, for instance, a perfect voltage source and a perfect current source are never going to exist. So you're always going to have some function of the other one. So you're not going to get perfectly horizontal and vertical lines. You're going to get slanted, if not even curvy lines. Same with the resistor R. This linear relationship that creates this perfect linear slope doesn't really exist, especially when you get to higher temperatures. Because as you put in more current into a resistor, the temperature goes up. As the temperature goes up, that changes the resistance. And you just keep spiraling this, and you start to get nonlinear forms for them too in practice. So I just want you to know in this case that right now for calculating things out for the circuits, we use these ohmic and linear approximations, and for almost all times they work. However, just know that there's some other things going on in the system, and we're going to look at some of those now, and non-ohmic devices and devices that don't necessarily have a linear IV relationship. So the fuse is a great example of a device that does not have necessarily a linear relationship. So what is a fuse? In this case, you see a fuse here. You can think of a fuse as a resistor that as more current is going through, it's getting hotter and hotter, and then it has a point where too much current goes through it, it gets really, really hot, and it melts and makes an open circuit. So why do we use this? We use this in case there's too much power going into something, or there's a short circuit, or we use it as protection usually to protect the voltage source. So in this circuit up here, we have a 100-volt voltage source. Maybe this is a really expensive voltage source, $100, $5,000, and we want to protect it. So with that voltage source, we have RS, which is the internal resistance of the source, which again, every voltage source has some kind of internal resistance. That's why whenever you short circuit a battery, it starts getting warm, because inside the battery there is an internal resistance. It's not a perfect 9-volt battery. It's a 9-volt battery with some resistance. And then after that, we put a fuse. And on the right-hand side, we have the RL, which is the resistance of the load, and the accidental short circuit. So let's just look. Let's just say this short circuit is open, like it is right now. If it's open, you can have that 100-volt source. All of that voltage and current is going to go through the resistance in the source, and then it's going to go through the fuse. It's going to go through the resistance in the load, and then back. And as long as that load is sufficiently big, as you're not going to burn out your power supply. However, let's just short that circuit. So we have that little arrow there. Let's connect it. If we connect it, we see that absolutely none of the current is going to go through that RL. It's all going to go through that short circuit down to the fuse. And so that, back to the source, not fuse, excuse me. So all of that current is going from the VS through the RS, which is inside of the battery, and then it's all going to the fuse and then directly down to ground. So this fuse is going to get really, really hot real fast. In order to protect the circuit, the fuse is going to break or trip. And when it breaks, it acts as an open circuit and no power can get through that loop again. It breaks the circuit right there. And that protects our 100-volt source from essentially breaking or over dumping too much current into that short line. So if you think about it, if you put a fuse on the top of a battery, so you take a 9-volt battery and I put a fuse directly on the top, you can see that fuse get warmer and warmer. It's going to start lighting up, getting yellow, and then, orange, and then yellow, and then finally that fuse is going to break. And the battery is going to be warm too, but it's not going to be completely empty, and it's not going to be completely fried as long as you selected a low enough fuse. And so that's essentially the relationship. If you select the correct fuse, you can protect your battery or your source from damage. And this goes really well for more high power electronics. So another one that we use a lot of fuses with is the electrospinning machine over in DEC. So that machine spits out between 8,000 and 40,000 volts of electricity. Um, and so 40,000 volts has a high potential for something to short circuit because that's going to essentially create a spark gap. It's going to be able to overcome the resistance of air in between the 2 points of the potential and ground. And so because of that, we put a lot of fuses into the electrospinning machine. And that hopefully protects it from, and some of the sensitive electronic from getting essentially shocked or having too much load go through them at once, and then they're fried and we have to replace them. So that's another place we use fuses. Fuses are used in houses too, and circuit breakers and trips. The older style is fuses, and they're little tiny, essentially little tiny metal wires in a little container that when you plug them in and too much current goes through at once, they heat up and then they break. And that protects your house from essentially having the wires heat up so much that they catch fire in the walls and your electronics in between catch fire, and that's to prevent fires essentially. So another example is if you, and don't do this, never ever do this, just going to put that out, but theoretically, if you took a hair dryer and you plugged it in and it was going on and then you dumped it in the bathtub, if you had no fuse in there or no circuit breaker, the wall power would continually dump electricity into that hair dryer, and you'd have a short circuit in there because the water would get in between the two resistive elements, and you would just be essentially dumping a whole bunch of current through that water, and you're actually going to create electrolysis, and you're going to break those individual water molecules up into their hydrogen and oxygen molecules, and you can get a whole bunch of different problems with this, including one, if you touch the water, there's a chance you can get electrocuted if you're grounding well. Two, that hydrogen and the oxygen is relatively flammable, and so you're going to get flammability problems. And then three, because you've cut out the resistive element, most likely, as long as water's gotten the full way inside of there, and there's some kind of ions in the water to make it conductive, that you're going to essentially damage some of the electronics in there, especially if there's any chips or whatnot, because those could be short-circuited because the water can go directly from the source all the way to ground. So if they're newer hair dryers with digital components in them, they can be broken as well. So the fuse is going to try to prevent a lot of that from happening, because as soon as it detects so much current is being dumped into that water, the fuse is going to tell the house, uh-oh, we have a problem here, we got to cut this off. And then it's going to cut the power by overloading that fuse. And then you're going to have to replace the fuse, which is a little unfortunate, but at least you're not going to have to replace the wires and everything in your house, most likely, as long as that fuse activates faster. So here we have a diode. This is another new component that we're going to learn about. The way I like to think of diodes in my mind is fancy one-way resistors. And so diodes have two parts. They look like resistors usually, except they have a single band on them, and I'll show you some pictures of it. But essentially, they have an anode and a cathode. And the anode allows your positive voltage to come into that side. The cathode faces the negative voltage or your ground supply. And as long as it's in that direction, current can flow through it. Now, if you flip the direction of it, theoretically no current flows through mathematically. In actual practice, you do get a little bit of back current, but we're not going to look at that. It's very small and it's not important for anything that we're going to do in this class. So if we look then at picture B now, B is the knee voltage, and essentially this is saying this is the voltage where current can flow through. So at a certain voltage, current's going to flow through, and before that, no current's going to go through. That's a mathematical approximation. If you look at C, you actually get the real diode here. And the real diode is going to be that curved line. And so that curved line is actually saying that there's thresholds in this LED, which means that, or in this diode, we're going to talk about LEDs in a minute, which means that current kind of increasingly flows the more voltage you get up to the point where essentially we have saturation, which is another term that we're going to look at soon. However, we can approximate this really well with that blue forward voltage there. And that blue forward voltage is essentially making our life really easy mathematically, saying any voltage lower than the forward voltage, you're not going to have any current flowing through, and then at that forward voltage, you're going to have all the current flowing through that you need. So we're going to look at this again more with LEDs and then again in lab, but just think they're fancy one-way resistors. If we look at the circuit up at the top here, we have a 5-volt power supply, we have a 100-ohm resistor, and then we have a little diode over there. And so, presuming that this diode is forward biased means it's, the way I think of it is forward biased, correctly oriented for simple circuits like this. If it's backwards, it's incorrectly, and that way an incorrect or reversed biased diode is not going to let current flow through. So a forward biased, good; reverse biased, not good in this case. That's how I remember it simply. It's not technically correct, but that's a good way to start. So with this simple circuit, we can do Kirchhoff's voltage law going around that circle. And so we have 5 volts minus IR minus VD. Or you can flip the signs to have minus 5 volts plus IR plus VD. And if we solve through that system, if the diode is forward biased, which means current can go through, the VD and the VD equals 0.7, then what we're going to have here is the ID, or the current through that diode, is going to equal 43 milliamps. And again, if I flip the direction of that diode, the current going through that wire, ID, is 0. So it's a resistor in one direction only. If you put it in wrong into a circuit, you're not going to get power flowing through it. So here we have a very special kind of diode called a light-emitting diode. So here we have a special kind of diode called a light-emitting diode, or LED. And you've probably seen this term and heard it many, many times. You probably have LEDs on lots of different electronics. So what we've got in picture A is the normal diode with its cathode and anode, and it's called the P and N. So which one donates and which one receives. And this is part of semiconductor physics, and we're going to get into that a little bit more. It's kind of cool just to kind of learn about how these work. But in a diode, current flows in one direction, not the other. Same with an LED. So in an LED, in picture B, we have a reversed bias diode. So this is saying that the diode is placed with the anode facing the positive on the battery source. So essentially this is facing the opposite direction, or the wrong direction, in order to generate light. And so if you take an LED and you put it into a circuit with the anode facing the positive of the power supply, it's going to behave like an open circuit. I equals 0. No current is going to pass through that. You can think of almost as having a giant hole in your circuit. Nothing is going to happen there. No light is going to show up. No power is going to be drained from that battery. You have an open circuit. It's like having two wires lying next to each themselves on the table, but never touching. So that's a reverse bias diode. A forward bias diode, however, is if you put the LED in, I think of it as the correct direction. And this is going to make light as long as VD is greater than VF, which means that the power supply is greater than the amount, the power supply has a voltage that is greater than the forward voltage, or the voltage to turn that LED on. So mathematically, if the LED requires 3 volts and you put only a 2-volt battery in front of it, that LED isn't going to turn on at all. In actual practice, these are nonlinear relationships, and because of that, you are going to see sometimes some slight dimming if you're underneath, a little bit underneath the forward voltage for that LED. So let's just say again, you need 2 volts to make the LED turn on, and you give it 1.7. Mathematically, that says the LED isn't going to turn on. In real practical engineering, 1.7 is going to make that LED turn on. It's just not going to be as bright as it could be without 2 volts. And so another reason, why do we use 2 volts then? Well, 2 volts is a mathematically and actually experimentally calculated voltage value that allows the LED to operate at the peak efficiency or the peak brightness without doing much damage to it, so it lasts a long time. And this is another way that LEDs last a lot longer than normal incandescent light bulbs because of the semiconductor physics behind them. So that's picture C. Right here, next we have picture D, which shows all the different colors with the forward currents and the voltages VF. So this is kind of cool, and I remember experimenting with this when I was learning about LEDs too, and I still remember it to this day. But LEDs require different forward voltages depending on the color. And this goes into some really cool and really deep physics that if you're interested, again, we can sit down and talk through. The physics behind this is not part of electrical engineering, but again, it's really cool to know. But what it comes down to is colors like blue, green, ultraviolet require a higher forward voltage than colors like red and amber, which means that the voltage drop over those LEDs is going to be more. So let's just say I have a 2-volt power supply. A 2-volt power supply on this chart means I'm going to easily be able to light up the reds and the ambers because their forward voltage is around 1.6. So I'm probably even going to have to put a resistor in front of them to drop it down a little bit. But with the yellow one, that's kind of around 2, and see the curve there, it's not a perfect linear relationship. So 2, we might get a little faint yellow glowing. And then if we go over to the green and blue, those are we're going to be so small on their forward voltage that we're probably not even going to be able to light them up at all. So green and blue are probably going to be off with a 2-volt power supply. And again, the forward current that we're looking at, which is the I in milliamps, usually we use 20 milliamps for LEDs. That seems to be a set standard. We can look at why that is too, if you're interested. But for now, you can kind of see that the green and blue LEDs are going to require a higher voltage than the red and amber LEDs. And there's another cool thought about this too, if you really want to tie this into a very general physics picture. Green and blue take more energy to produce. And so the way that the semiconductors physics work out, because if you look at 20 milliamps going across there, a power equals voltage times current, and so 3.3 times 20 milliamps is going to be a greater value than 1.6 times 20 milliamps. So that's another interesting thing we can do, again, by looking at these plots. The final thing I want you to see about this plot that I've repeated before, but I want to emphasize is anything over 20 milliamps, it looks pretty linear. Very linear, actually. Anything under 20 milliamps looks very curvilinear, and that doesn't approximate nicely linearly. So this is another reason with these curves why the LEDs don't just immediately turn off if you're slightly underneath the required forward voltage. That's why you get dimming. So that's another interesting part about this too. So let's look at E. And so an LED equivalent circuit that we can do, and the circuit diagram or the circuit symbol is on the left there with the diode with a circle around it and a couple of zigzags coming out, or sometimes you have 2 arrows coming out to indicate light, and that shows an LED. But if we want to mathematically calculate this out, we're going to mathematically calculate this as a diode with a resistance. And the diode is going to be the forward, or if you're trying not to turn the light on, a reverse bias diode. And the RD is going to essentially be the resistance of that LED, or the resistance there. And resistance is going to come from the fact that A, LED is heating up a tiny bit. It's not heating up very much compared to incandescent light bulbs. So the light bulbs, the incandescent ones that we used to have with the filament inside of it, 80% of the power that went into them was heat and 20% was light. So they're very inefficient, as opposed to LEDs, which are the opposite almost, where 80% of the power going into them comes out as light and 20% efficiency. So the light and the power are going to contribute to the effective resistance RD that we're going to be able to use in the LED for circuits calculation. So a lot of info on this slide, a lot of cool stuff about LEDs. I'll post another link or two if you want to read up some more on your own about how LEDs work. And we're going to do a lot of labs with them too, because LEDs are a really nice way to be able to show if your circuit is working too, because you get to see visual feedback immediately if you've put your reverse bias diode in, or your forward bias diode, or if you're looking for a certain amount of voltage. You can even use LEDs, if you're kind of clever, as a very simple analog way of showing voltage. Because, again, they each have a different forward voltage. So if you put a bunch of these together next to each other in parallel with a sufficient current supply, they will light up, and you'll be able to look at, okay, if red and amber are lit up, but yellow, green, and blue are not, we know that our forward voltage is somewhere in between 1.6 and 2. And that's a nice way of being able to do a very quick analog analysis without doing any microprocessors or programming to be able. So here we have a neat example, example 215, which is using a square wave power supply. So it's a voltage source that changes positive and minus up and down. And then also it has two diodes in it. And the diodes, one is forward bias and the other is reverse bias. So what this is asking is to generate the plots of what the current through I1 and the current through I2 look like at given times. And so we're going to be able to work this one out. This is kind of a fun one actually to do, because again, it's an interesting circuit. We're going to see in the next proof that it's actually a blinking back and forth circuit between two diodes or two LEDs or whatnot. And the LEDs are going to have different brightnesses based on the resistances. So let's get into it.